Start now with okay, to start the day on a celebration note, we, as most of you noticed, there was an option to apply for this paper award for the Minorities in Economics Committee established award for best paper on issues related to discrimination, inclusion, diversity, integration, etc. And we received a lot of interesting papers. First, the Minorities in Economics Committee group read all of them, and then as a chair of the committee, I with Gemma, we established also a final selection committee for the finalists that included also our former President Oriana Bandiera, representing also the founders from the LSE hub, and one other professor in Germany. And at the end of the day, we are happy to say that it was a very tough choice, very interesting papers. And so the prize goes to the paper by Timothy Bond. So Timothy Bond is the winner on a very important topic. So there is a literature, of course, already on equilibrium statistical discrimination. But this paper is very interesting because, first of all, it has the theoretical mechanism about how this equilibrium statistical discrimination can come about in a specific context, and then looks at important administrative and survey data to confirm the mechanism. So compared to the theoretical literature of an equilibrium statistical discrimination, this focus on a specific mechanism is very important for future research as well. And, the specific context, I don't have time, of course, to describe it, but think about it in this simple way. So we know that there is statistical discrimination of blacks in American, labor market and other contexts. Well, one mechanism that he studies, theoretically and empirically, it could be that in order to compensate for the expected discrimination that blacks can find on the market, then they try to overcompensate by choosing harder majors in school. But because they choose systematically harder majors in school to try to compensate effectively, then it becomes like a self-fulfilling prophecy that those with similar characteristics who have made an extra effort to go above their range of capacity to compensate the statistical discrimination end up being, rationally treated differently by the firms, which is not to say that the firms do not exercise also taste-based discrimination and all that, but it's a very interesting mechanism that is very important for future research on affirmative action policies, etc. Congratulations, Timothy Bond, if you're here.
Is Timothy here? Come over, please. You can give it.
Hope I made justice to your contribution.
Okay.
Thank you.
Hold on, not yet.
Again.
Thank you.
And thank you for
very much.
Congratulations, Timothy. Thank you, Massimo. Congratulations, Timothy. I should also say there was a runner-up, Diego Sambiasi. As Massimo was saying, it was a tough choice, so there was very good submissions. We also have a second prize. It's given to 3 papers, which is the prize for the Best Young Economist. It's the Young Economist Award. This is an award that's been going on for quite a few years. It's sponsored by UniCredit, and it basically rewards the best papers by the program committee. The program committee selects the best paper of young economists. The 3 awardees, and if you hear your name, please come up. Gemma hasn't told anyone who the winners are, so there's a little bit of suspense here. The first, by the way, they're in alphabetical order. There's no first, second, third. The alphabetically first paper is on the sources of regional variation in intergenerational mobility by Lieke Bekers. The second one is on the symbols of oppression, the role of Confederate monuments in the Great Migration by Francesca Ferlanga. And the third one is the clean transition in a network economy by Shane Maughan. Lieke, Francesca, and Shane, please come over. Congratulations. Congratulations, everybody. Okay, thank you, everybody, for turning up so early. It's much easier because we have a wonderful speaker. We have a wonderful lecture to come up. So Marina Halac doesn't need any introduction. She's the Stanley B. Razor Professor of Economics at Yale. She got her PhD from Berkeley in 2009, was a professor at Columbia and briefly at Warwick as well, before joining Yale in 2018. She's currently the co-editor, one of the co-editors of Econometrica, and next year in 2025, she will become the main editor of Econometrica. She was previously a co-editor of Theoretical Economics. Whatever I hear people talk about her editing work, people want her everywhere. So she's an amazing editor. Both authors, referees, people in the profession love the work she does. And it's a service to the profession, so we are all very grateful for that. She's a fellow of the Econometric Society, now also of the European Economic Association, and she's an economic theory fellow. She received teaching prizes. She received the Elaine Bennett Research Prize from the American Economic Association, which is given or recognizes and honors the outstanding research by a woman not more than 10 years beyond her PhD. She has impressive research. If you look at her papers, each of the papers is powerful, has an important contribution. Her field, when I'm trying to define her field, is not so easy. It's theory. It's, you could say, game theory, contract theory, you could say mechanism design, but it's broader than that. You know, the papers are obviously very well published. They're in all the top journals, but she applies that kind of broad set of ideas to micro questions in particular, or specifically relational contract is one big theme in her research. Teams and organizations is another theme in her research, and experimentation is a theme. But she also, and this is, I think, the kind of an interesting approach of this theory, is that she also applies this to traditional macro questions. She's an Argentinian economist. If you're Argentinian, you have to do macro, otherwise they might revoke your passport. But she applies these ideas from theory that, you know, she manages very well, she understands very well to, you know, some of these big macro questions. And there she talks about rules versus discretion in fiscal policy, a very kind of, you know, traditional problem in economics. Financial crisis, of course, Argentina gives her the data for that. And then inflation and monetary policy. What I appreciate most about her work is precisely the fact that these boundaries that exist between different, you know, pigeonholes, if you want, in the profession, that she blurs those. And I see two dimensions in that. First of all, this distinction between macro and micro doesn't really exist, because there's agents who optimize, and if you have many agents that might interact through markets where there's equilibrium, there may even be externalities, you see aggregates. And, you know, going from micro to macro is really, there's no distinction. I mean, it's all individuals that jointly lead or can have an outcome that's the macro outcome. And the second distinction is between this idea of theory and applied work, okay? Because, you know, sometimes it's kind of, you know, what is pure theory? I mean, she does pure theory, but always, very often in her problems, things about applications. And I think this is fascinating also as a reader to try and understand how this powerful theory can help elucidate many issues that we see around the world. I asked her, one of her advisors, Steve Tadelis, to tell me something about her. He wrote a very long email, very generous. Let me just read one line out of this email. He said, her enthusiasm and passion for research was nothing I've ever seen in any of my other students, either before or since. As a father, I say you should never compare your kids. As an advisor, you shouldn't compare your advisees, but I mean, if it's so obvious, there's nothing you can do, you know. So, and if she wasn't even perfect enough, I learned just recently that she used to live for a while in Ghent, Belgium, a few kilometers from where I grew up. So, you know, now she's even more perfect. By the way, for the locals, if you want to ask questions after the talk, you can do in Dutch. She perfectly controls that. So, without further ado, here's the Marshall Lecture for today, Marina Halac.
Okay, thank you so much. That was overly generous. So Jan said yesterday that he would tell some lies, so he continues to tell lies, starting with me speaking Dutch. Please don't try. But yeah, thank you so much. I'm delighted to be here. Thanks everyone for joining, especially this morning after the party last night. So extra points for all of you who woke up early. So I'm going to tell you about contracting for coordination. This is an agenda I've been pursuing in the last few years, and I'm very excited to tell you about it. So we are going to be talking about the coordination problem. So I want to think about the situation where there are multiple agents, and because of some interdependence, some externalities between the agents, they should be acting in some consistent way, but they face strategic risk. So they have to choose their actions without knowing the actions of the other agents. And I want to think of a principal who wants to coordinate these agents to choose certain actions. So the principal will be contracting for coordination, and she will want to address the strategic risk that agents face. I will try to convince you that these problems are important for a variety of applications. We can think about applications within organizations when we think about incentives in teams. I have this nice quote from Milgram and Roberts saying that the key role of management in organizations is to ensure coordination. And we can think about applications in markets. We can think about firms raising capital from multiple investors, trying to coordinate investors who invest in their projects. We can think about firms selling goods with network externalities. We actually discussed network externalities yesterday at the end of Jan's presidential address. And this is also a setting where we are going to have contracting for coordination. And surely we can also think about applications to macro, and that's coming in the future. So here is the basic structure of the problem that I want to study today. I'm going to think about a principal who contracts with a set of agents. The contracts that the principal signs with these agents are going to induce a game between these agents. And because of the nature of the coordination problem, this game may have multiple equilibria. So a key question for us is how we are going to deal with that equilibrium multiplicity. The standard approach in mechanism design has been to assume that our principal, our designer, is very powerful, and she can pick the equilibrium that agents are going to play. So she's going to pick her preferred equilibrium. But we have no idea how the principal would select an equilibrium when we have this multiplicity. So here we want to take the exact opposite approach. We want to think of a principal who is very conservative, and she's concerned about the possibility of these bad equilibrium outcomes. So she will want to guarantee herself a high payoff. She will want to maximize her payoff in the worst possible equilibrium outcome that may realize in this game that we are inducing between the agents. And we are going to see how this concern for strategic uncertainty, for strategic risk, is going to provide predictions about the contracts that the principal will want to offer to these agents to ensure coordination, and also about the outcomes that are going to realize. Okay, so rather than telling you about one paper, what I'm trying to do today is to convince you that these problems are important for many different settings. So I want to tell you about different settings. So this is how I'm going to structure the talk. I'm going to start with a very simple setup where actions are contractable and the externalities between the agents are exogenously given. This is going to be a little bit abstract, but then we're going to move on to applications. I'm going to think about an investment problem where the externalities are endogenous. Then I'm going to be thinking about a setting with hidden actions, moral hazard problems, thinking about incentives in teams, and I'm going to talk about public and private contracting. And finally, if I have time, I hope I can tell you a little bit about a problem where we have incomplete information, hidden types, which is going to be very important when we think about the monopolist problem and hence goods with network externalities. I won't be able to give you a lot of details about each of these setups, of course, so I'll try to just focus on some of the main insights and takeaways and the main intuitions. Okay, so for the first part, I'm going to be building on the work of Ilya Segal, so let me give you a setup here. So we're going to have a principal who contracts with a set of agents, a set N of N agents. I'm using notation a little bit. Each of these agents is going to choose a binary action. So action 1 means participate in the principal's mechanism. Action 0 means not participate. The principal can sign bilateral contracts with these agents. So for each agent, the principal can offer a payment for participation. If you participate, you get this payment. And so given an action profile, so an action for each agent, here I'm writing what is the payoff to an agent. So an agent gets a payoff that there is some utility there that depends on the whole action profile. So that's where the externalities are going to be present. And then if the agent participates in the principal's mechanism, he's going to get this payment omega. So as I said, this first part is going to be a little bit abstract, but bear with me, it's going to be quite simple. A scheme, so the payments that the principal is going to offer to these agents is going to induce a game between these agents. This is going to be a simultaneous game, so agents are choosing whether or not to participate simultaneously without knowing the participation of other agents. And the payoffs are given as I just described. The solution concept is going to be Nash equilibrium, and so an action profile is a Nash equilibrium if the prescribed action for each agent is the best response to the prescribed actions to the other agents. Now, the principal wants to guarantee that all of these agents participate. Okay? So she wants to coordinate these agents to participate, and she doesn't like paying the agents, so she wants to do that at the least possible cost. So what does it mean to guarantee that they participate? Again, because of the coordination of the externalities, we should be worried about multiplicity of equilibria here. So the principal wants, at the least possible cost, implement this full participation outcome as the worst case Nash equilibrium of the induced game. As the, in this case would be the unique Nash equilibrium of the induced game. So she's concerned with these worst case outcomes because she's conservative. All right, so let's be a little bit more formal. I'm going to define E of omega, the set of Nash equilibria under scheme omega. And so the worst case implementation constraint is basically telling us that if we add any epsilon to these payments omega that the principal is offering to the agents, it has to be that the set of Nash equilibria is a singleton and is given by this profile where everyone chooses to participate. This epsilon is simply because of a technical complication. It's a nuance that we are optimizing over an open set, so you can ignore it. All right, so now I just wanted to write the principal's problem formally. As you can see, it's a very simple problem. The principal is choosing a scheme, namely a payment that she's going to offer to each of these agents. She wants to minimize the sum of payments. She doesn't like paying the agents. And she wants to satisfy this worst-case implementation constraint, namely guarantee that everyone is going to say, yes, I participate in this mechanism. Very simple. Okay, so at this point, I want to distinguish between two scenarios. One is where the externalities between these agents are increasing. The other one is where the externalities are decreasing. So this is, everyone knows what this means. Externalities being increasing means that the gain in utility that an agent gets from participating versus not participating is increasing in other agents' participation. So my incentive to participate is increasing in the other agent's participation, so I would have a game of strategic complementarities. Decreasing externalities means exactly the opposite, and then that would give us a game of strategic substitutability. Most of the applications we are interested in are going to be games of strategic complementarities. Okay? So I'm going to be telling you about the first three in this list: an investment problem, a teamwork problem, the problem again of a seller selling a good with network externalities. These are all cases where we have increasing externalities. Those are the three I'm going to be telling you about, but the literature has studied many others. There is an older IO literature going back to the work of Innes and Sexton that studies exclusive dealing contracts. Of course, in finance, many people have studied the problem of bank runs. These are all examples of strategic complementarities. And in fact, these are the interesting applications we want to think about. But before we do that, I'll tell you why the case of decreasing externalities is not very interesting for what we want to do today. So in this slide, I'm defining this scheme that I'm calling omega Nash equilibrium. This is the least cost scheme for the principal that induces these agents to participate as a Nash equilibrium, but not necessarily the unique one. Okay, so basically what the slide says is that this payment makes every agent indifferent between participating and not, given that they conjecture that everyone else will participate. What the proposition says is that if I have a setting with decreasing externalities, this scheme not only induces full participation as a Nash equilibrium, but it also guarantees that it's going to be the unique one. Because if an agent is willing to participate when everyone else does, then he's also willing to participate when fewer other agents do, given the decreasing externalities, right? And so this worst case focus that I started with, and I said, okay, this is the big thing today, has no bite here. Okay, so if we have a setting with strategic substitutabilities, we have nothing to say. But what happens if we have strategic complementarities? Well, clearly things are going to be different now, because I may be willing to participate, given that I expect everyone else to participate. But if I think that Jan won't be participating, now my incentive to participate is lower, right? And so that scheme that we just defined may not be enough to guarantee the participation of the agent. So let's go to a simple example. I'm going to be using a lot of simple examples today. Let's just think about two agents. And so if an agent participates in the mechanism and the other agent does as well, then the disutility from participation is just 1. But if the other agent doesn't participate, then this agent suffers a disutility of 2. So she would prefer to participate when the other agent participates as opposed to not. And if I don't participate, I get 0 disutility. So this is a setting where if I offer a payment for participation of 1 to each of these agents, I can get a Nash equilibrium where they both participate, right? Because if I expect you to participate with a payment of 1, I'm happy to participate. But the problem is that I would also have another equilibrium where neither of them participates. Because if I expect you not to participate, I demand a payment of 2 to participate. It's very simple. But let me convince you that this nice equilibrium that they both participate is very fragile, right? So maybe I think that Jan would like to participate, but I'm worried that he thinks that I don't want to participate. And so because he thinks that I won't participate, now he doesn't want to participate, right? So you can think about these higher order beliefs, and this equilibrium breaks down. Okay, so it's not clear how we can guarantee that this is going to be the equilibrium if these are the payments we are offering. So what can the principal do? She wants to ensure that both agents participate. She suffers a very large negative payoff if there is no participation by either of the agents. So what can she do? Well, for sure, she could offer a payment of 2 to each of these agents. That would say that we are making it dominant for each of them to participate, right? That ensures 2 plus epsilon. I'm ignoring these epsilons, okay? So let's forget about the epsilons today, but it would be 2 plus epsilon. That would ensure that both agents participate, but that would be quite expensive. And that's not necessary, right? I could offer a payment of 2 to one of these agents. So let's say that this is Jan and me, okay? Let's offer the nice payment to Jan. That makes sure that he participates. That pins down his action choice. But now I know that it's dominant for him to participate. If the principal offers a payment of 1 to me, I'm going to be willing to participate. So we can just offer a large payment to one of these agents, pin down this agent's action choice. That provides assurance to the second agent, and now we can offer a lower payment to the second agent to ensure participation. And so this is an example of something more general that we can show here. I'm going to define these ranking schemes. When I say that a scheme is a ranking scheme, if there exists some permutation of the set of agents, some ordering of the set of agents, such that each agent in this permutation, given these payments that we're defining, is going to be indifferent between participating and not, when he conditions on everyone else coming before him in the permutation participating, and everyone else coming after him in the permutation not participating. So I just think of ordering the agents according to some order, and each agent in this order says, well, if everyone that comes before me is participating, but everyone else is not, then I'm exactly indifferent between participating and not. So we are making iteratively dominant for these agents to participate at the least possible cost. Okay, so the first agent finds it dominant to participate, the second agent finds it dominant given that the first agent is participating, and so on and so on. And here is the result that I'm going to be using for the, today for everything I'm going to be doing. I'm going to be calling this the ranking lemma. The ranking lemma says that every ranking scheme satisfies the worst case implementation constraint. So namely, if I add these epsilons that I wanted to ignore, I will be guaranteeing participation with the ranking scheme. And moreover, any scheme that satisfies this worst case implementation constraint is going to be weakly dominated by some ranking scheme. So this is a very powerful result because it's telling us that in a setting with increasing externalities, if I want to solve for an optimal scheme to ensure this coordination, I just need to look within the class of ranking schemes. Okay? I don't need to worry about other types of schemes. And so now we can say that if we have a setting with increasing externalities, the optimal scheme takes this form. It specifies some permutation, pi star, of the set of agents, and some payments, omega star, such that, again, each agent in the permutation is indifferent between participating and not when those preceding him participate and the rest do not. Now, this is not how the agents play the game. The agents are choosing their actions simultaneously, but this is how we describe an optimal mechanism for the principal. And as I said, this is quite abstract, I know, especially for 9 a.m. But we can already get some insights from this very abstract setting. And so here is an important insight that we get. This proposition says that if we have increasing externalities, the optimal scheme is going to be discriminatory. So we were talking about discrimination just now when we gave one of the awards. I should be very clear about what I mean by discrimination because I'll be talking about discrimination today as well and about inequality, but we should be clear about the definition. So discrimination today for my talk will mean that we have two agents who are identical, they're completely symmetric, and we treat them asymmetrically. Okay, so we offer them different contractual terms. And so if we have agents who are identical, so here they will have the same utility function that I defined, right? What this proposition is saying is that the optimal scheme is going to offer them different payments. Why is this? Well, we know the optimal scheme is a ranking scheme. So, we know we are going to define some permutation of the set of agents and the payments the way we described. Now, if agents are completely identical, the permutation is completely arbitrary, right? The agents are all the same, so all the orderings are the same, but I'm going to pick some ordering. And then agents who are placed earlier in the permutation, I'm making it dominant for them to participate, conditional on fewer other agents participating compared to those who are placed later in the permutation. So they are going to demand a higher payment to be willing to participate. Jan should be given a high payment to be willing to participate when I don't, but then given that he's participating, I get a lower payment. Right? I'm not saying we're identical, but so it's not a great example, but if we were, then we would have discrimination. We'll talk about the case where we are heterogeneous. I can use Jan again. And so we already get here that, we have this discrimination result. And let me emphasize that this discrimination result arises from this concern for strategic uncertainty that this principal has, and of course, the principal's desire to minimize her cost. Right? If the principal was not concerned about the possibility of bad outcomes, as we said, we could offer this Nash equilibrium payment scheme that I defined, right? And that scheme would treat identical agents equally. But because of this concern for strategic uncertainty, we are going to be discriminating between the agents. Okay, so now I'm going to move on to more applied settings. And the next thing I want to tell you about is some of the work that I've done with Ilan Kremer and Eyal Winter, where we apply some of these ideas to an investment problem. So here we want to think about the principal being a firm, the agents being investors, and this firm is raising capital from these different investors. So the idea is that the firm has some project, it's a worthwhile project, but it needs capital from different investors to get implemented. And let's say that the project can be implemented only if the amount of capital that is raised is above some stochastic threshold. Okay. So I can think about the probability of project success, let's call implementation success, as being a function that maps from the amount of capital that I raise, right, to some probability. Let's take that function to be strictly increasing, so the more capital I raise, the more likely is that we can get to implement this project, of course, and for today's talk, let's assume it's log concave. If the project gets implemented, namely success, then the principal get some very large payoff, and the principal can use this revenue to offer returns to these investors for investing in the project. Okay? And let's say that each agent, each investor has some capital endowment, as I'm defining here. So what are the contracts now that this firm can offer? So the firm will approach each investor and say, well, I want you to invest this amount of capital in my project. Of course, this amount of capital cannot be larger than the endowment of the investor. And then the firm can also offer some returns. If you invest, I offer you this return. Let's assume for today, to simplify things, that the firm can only offer returns in the case that the project indeed succeeds, which is when the firm has money to pay the investors. Let's assume we cannot ask the investors to pay the firm beyond the capital they invest, or some limited liability. All of these things could be relaxed, but it doesn't matter for today. Okay? And so we offer these returns in the case of investment and success. And so now we had these binary actions. What do they mean? Well, now action 1 means that this investor says, yes, I invest this amount of capital that you want me to invest in your project. And action 0 means, no, I don't invest. Instead, I invest this amount of capital in some safe asset that pays some risk-free rate. I'm calling it theta. Think of all of these returns in percentage terms. Okay, so we can now rephrase the problem that way. And we can, of course, write what would be an investor's expected return on this amount of capital, as I have it here. If the investor decides to invest this amount of capital with the firm, then he's going to get this return that he was offered in the case of success. The probability of project success, of course, as we said, depends on the total amount of capital that the firm raises from all of these investors. If the investor instead decides to invest this amount of capital in the risk-free rate, then that's the interest that he's going to get. And so you can see here that we are going to have increasing externalities, because my incentive to invest in this project is going to be higher the more other investors choose to invest, because that means that the project is more likely to be successful, and hence I'm more likely to be paid a return. And so that's why we think the investment problem is typically a game of strategic complementarities. Okay, so now how do we solve this problem? Well, we can follow this two-step approach. I teach this contract theory course, and in my first class, I always say, if you have a paper where you can follow a two-step approach, follow a two-step approach. I love that. So first, we fix what are the amounts of capital that we raise from these investors, and we solve for what are the optimal returns we want to offer to the investors who raise this amount of capital. Once we know what is this optimal return scheme, we can solve for the optimal amounts of capital we want to raise. So let's focus on step 1. Let's fix what are the amounts of capital we want to raise. And now we have a problem that looks very similar to what we were describing before, even though there are these differences. We want to think of the principal offering these returns, in the case of success, to these investors, conditional on them investing. She wants to minimize the returns that she has to offer. This firm also doesn't like paying agents. And she wants to ensure that everyone says yes. Everyone says, yes, I invest the amount that you want me to invest in your firm. Okay, so I have this worst case implementation constraint again, saying that I want this to be the worst case or the unique equilibrium that everyone chooses to invest with. So let's go to an example. Let's suppose that we have the risk-free rate is 10%, pretty nice. We have just 2 investors. One of them has $10 to invest, the other one has $20. And let's say the probability of project success is given by the amount of capital that is invested, X, divided by 30. So this would be like this stochastic threshold would be uniform between 0. So I made it simple enough so that if both of the investors invest their capital with the firm, the project succeeds for sure. So that means that if the firm tells the investors, I give you 10% in the case, if you invest with me, the success will happen for sure if both of them invest. I'll have a Nash equilibrium where both of them invest, right? So with 10% on their success, there is a Nash equilibrium where both of them say, yes, I invest with the firm. But as we know, there are going to be other Nash equilibria because of the strategic complementarities. There is a Nash equilibrium where both investors say, no, I don't invest with you because I don't think the other investor will invest. Then I don't want to invest because 10% is not enough. The project may not succeed. I'd rather get 10% for sure by investing in the risk-free rate. Okay, so this is very similar to what we said before. But now let's think about what happens here. If I had that these 2 investors were identical, as we had before, so they each has $15, okay? Now we know we can apply our ranking lemma. We know we would discriminate. One of them would get a very nice deal, a high return. The other would get a lower return. But now let's think a little bit more dynamically. Fine, we can do that. But what happens next period? Now one is richer than the other. This case where they are identical doesn't last long, right? One got a high return, the other one got a low return, so now one has more capital than the other. So I'm not looking for a discrimination result. I know I would get a discrimination result, but now I'm interested in inequality. Now I have investors who are not identical, they are heterogeneous. And I know that my ranking scheme is gonna be offering better terms to some investors compared to others. But now I have a new question to ask, which is who's gonna get the better terms? Is it gonna be the large investor who gets the better terms, or is it gonna be the small investor who gets the better terms? So this is about inequality rather than discrimination. So let's look at the example. We have to make it dominant for one of the investors to invest to rule out this bad equilibrium where neither of them wants to invest. So suppose we make it dominant for the small investor. Okay, so the small investor says, well, if I'm the only one investing, the probability of project success is only 1/3. So she's going to demand 30% return to be willing to invest with the firm rather than putting the money in the safe asset. So the firm would have to offer 30% to the small investor, then the firm can offer just 10% to the large investor, same idea as before. And so the cost to the firm would be equal to 5. It turns out that the firm can lower the cost of guaranteeing investment by making it dominant for the large investor to invest rather than the small investor. The large investor is the only one who invests. The probability of project success is 2/3. So the large investor is willing to invest no matter what the small investor does if he's offered a return of 15% on their success. So then I can offer 15% on $20, 10% on $10. The total cost went down to 4. So this is not just in the example. This is going to be a more general result. And I'm going to derive it by applying our ranking lemma, but now apply it in this setting where I have heterogeneous agents. And so we have a supermodular game. We can apply the ranking lemma. The proposition says that an optimal scheme is going to specify some permutation of the set of agents, again, some ordering of the set of agents, and return such that each agent in the permutation is indifferent between investing and not when those preceding him in the permutation invest and the rest do not. Okay, so it's the same idea, and here I just wrote the formula for what that return would be. But now, moreover, we get that this optimal permutation is one that is going to order these investors by decreasing size. So larger investors are going to be placed earlier in the permutation compared to smaller investors. And what that means is that larger investors are going to get a higher return than smaller investors. This is a higher net return. So this is not that they just get a larger dollar amount. They get a higher return per unit of capital invested, per dollar that they invest. And so here I should say, actually the evidence that we cite in the paper is about private equity. Jan yesterday was saying, be careful with private equity. So there is evidence here that larger investors indeed get better terms than smaller investors. Part of the story sometimes we think is about information. Larger investors know which investments are better than the smaller investors, but there are empirical papers there that condition on the investment. So even for the same investment, larger investors get better deals. So let me try to go back to the example now, give you a little bit of intuition. So this is the same example that we saw before, and what I'm drawing here is this return that we solve for. This is the return that we are offering in an optimal scheme as a function of the total capital that has been invested, right? That we are conditioning on. And so what we can see is that the return that the firm has to offer is going to be decreasing in the capital that is invested, of course, right? The more capital is invested, the higher the probability of project success. But what's interesting about the graph is that this curve is going to be convex. So the return that I have to offer decreases as more capital gets invested, but at a decreasing rate. What that convexity should tell you is that you want to move down this return curve as quickly as possible in order to minimize the sum of returns that you are paying to these investors. So if we are making it dominant for the small investor to invest, if we are offering the nice deal to the small investor, this is how it would look like. But if we are offering the nice deal to the large investor, I can move down this return curve more quickly. And because I'm compensating investors on the marginal unit of capital that gets invested, that's exactly what I want to do. Another way to think about it is that the large investor, because of his larger amount of capital, he has more self-insurance, right? So the investor with the $20 knows that $20 will get invested as opposed to 10. And that larger self-insurance is what makes it cheaper for the firm to guarantee investment by offering the nice deal to the large investor as opposed to the small. So now, if you think about dynamic capital markets, what we have identified here is a mechanism that is going to exacerbate any inequalities across these investors. To be clear, I'm not advocating for this. I'm not saying this inequality is good. The first time I presented this, there was a question in the audience. It's like, are you no, for sure not. But what I'm saying is that here is the mechanism. I'm just looking at the optimal mechanism for the firm. And all I change from a very standard problem is to say, look, this firm doesn't like the outcome not being determined, right? Like the firm doesn't like that any equilibrium here, we have different equilibria that may realize. The firm wants to make sure that there is investment. I need to raise this capital. And so just by doing that, we have identified this mechanism that is going to give us this exacerbation of inequality in these capital markets. Now, I've done everything by looking at these capital amounts that I want to raise, but if I want to talk about inequality, actually I should be thinking about the wealth of the investors, so I should be thinking about their capital endowments. And so that's the next thing that we do. I mean, we do many other things in the paper I won't tell you about, but let me just mention here that we have this majorization result here that says that this firm benefits from these investments being as dispersed as possible. And so the firm wants this capital to be concentrated in the hands of fewer investors, right? And so what this means in terms of the capital amounts that we are raising from the different investors is that the firm would like to go to the wealthiest investor, raise all their capital, then go to the second wealthiest investor, raise all their capital up until some point. And so indeed, the investors who are investing larger amounts of capitals are those who are wealthier, right? So that was kind of the assumption behind what I said about inequality, and that is indeed true. And moreover, what we get is that small investors not only get worse deals when they get to invest, but also sometimes they're excluded. So they get worse investment opportunities. That's also something that we see in the evidence. And part of what I'm trying to do here is start with a very abstract and simple setting and try to convince you that when you go to applications, there are lots of interesting questions you can study. And so here there are even more, right? I could allow this firm, I could say the firm does have some initial capital, so the firm could offer returns even when the project doesn't get implemented. Then I can think about the portfolios of, the risk profiles of the different investors, who's going to get higher risk, higher return, lower risk, lower return. There are lots of interesting questions you can study. Once you apply these tools to an application, you start thinking about more and more questions. But I do want to tell you about the other settings, so I'm going to stop here. So the next thing I want to do is move to organizations. As Jan said, as I've been interested in organizations for a while. And when we think about organizations, we think about teams and how to incentivize teams. And what is going to be different here is that in teams, we have agents choosing effort, and these effort choices are going to be hidden. So these are settings with moral hazard. I can no longer contract on the action, right? So before I was offering a return conditional on you investing, I cannot condition on the effort choice because that's not observable and verifiable. So I'm going to start by telling you about the seminal work by my co-author Eyal Winter, this beautiful paper called Incentives and Discrimination. And so here we're going to be thinking about this principle. This is a manager in an organization, and she wants to induce a team of agents to exert effort. So our binary action now is going to be either work, that's action 1, or shirk, that's action 0. And again, that's a hidden action. And working is costly for the agents. So here we have a cost of CI for each agent I, which is strictly positive. The only thing that we can observe here is whether the team's project succeeds or not. And let's assume that project success depends on the number of agents who choose to work. It's going to be an increasing function, so effort is productive. The more agents who choose to work, the higher the probability of the joint project succeeding. Let's also assume that this function is convex. Convexity will mean that we have increasing externalities, right? It will mean that the marginal product of effort for any one agent, so the contribution to project success from choosing to work rather than shirk, is going to be increasing in the effort choices of the other agents. I'm going to assume limited liability, and so the only thing the principal can do here is offer a bonus payment to each one of these agents conditional on project success. And so that's what a scheme is going to define. So agents are choosing their effort choices simultaneously, given the bonus payments that they receive and given an action profile. This is the payoff to an agent I. The agent is going to get the bonus if the project succeeds. Again, this is a function of the number of agents who choose to work. And he's going to bear the cost of effort if he chooses to work himself. Again, because actions are not contractible, now notice that this agent may get this bonus payment even if he's not working, right? Because if the joint project succeeds, he's getting the bonus payment. All right, so now I can write my problem. I have my worst case implementation constraint. The principal will choose a bonus scheme. She wants to minimize the bonuses that she's going to pay to these agents. And she wants to guarantee that everyone is going to choose effort. By the way, I'm always saying everyone is going to choose effort, everyone is going to participate, everyone is going to invest. You can think that I already decided what is the team of agents that I want to induce to choose effort, right? So this is like the second step of a larger problem. And as it was true before, I'm paying these bonuses only in the case of success. And as it was true before, I didn't mention it here, the principal is conditioning on this probability of project success being such that everyone is going to be choosing to work because that's what I'm uniquely implementing, right? So as the principal, I know that's going to be the outcome here. All right, so this looks very similar to what we had before. Let's go to an example because I'm going to be using this example later on as well. So again, I want to think about two agents. This is the story I want you to have in mind. We have these two agents. Each of them is going to work on an individual task. If an agent chooses to work, to exert effort, he completes his task for sure, with certainty. But if an agent shirks, he completes his task only with some probability alpha. We cannot observe individual task completion. We can only observe whether the joint project succeeds or not. And the joint project succeeds if and only if both agents complete their task. So if both agents work, the project succeeds for sure. If one agent works and the other one shirks, the project succeeds with probability alpha. If both agents shirk, the project succeeds with probability alpha squared. Okay? Very simple. So if I want to induce both of these agents to work in this team, as a Nash equilibrium, I'm not concerned about strategic uncertainty, about multiplicity, and I want to do that at the least possible cost. This is the bonus that I would offer to each of them. It would be the same if they are identical, if I have the same cost of effort as I have assumed here. So I'm calling this the low bonus payment. This low bonus payment makes an agent indifferent between working and not when he conjectures that the other agent will be working, right? So it's equal to the cost of effort divided by the marginal product of effort when I take the other agent to be working. So my contribution to project success, if the other agent is working, is that I increase the probability of project success from alpha to 1 when I decide to work rather than shirk. Okay, so that's very simple. But we know already that this is not going to be enough. We have a setting with increasing externalities. And so that means that we'll also, if we offer this bonus payment to both agents, we'll also have another equilibrium where both of them choose to shirk. Okay? If I think that Jan is not doing his share, I don't want to do my share here, right? It's very unlikely that my work is going to be enough for project success, so this bonus payment is not going to be enough for me. So what do? Same thing as we said before. We have to make it dominant for one of these agents to work, so we have to offer a large bonus payment to one of them. So this is the high bonus. The high bonus is given by the cost of effort divided by the marginal product of effort when the agent conditions on the other agent not working. So the agent who is offered this bonus now says, I don't care what, if I'm offered this bonus, I don't care if Jan is shirking here, I still want to work, right? This bonus is high enough for me that I want to work. But now, given that I'm working, this provides assurance, right? So given that I'm getting this high bonus, that provides assurance to Jan, and Jan says, well, even if I'm offered the low bonus, I also want to work. And so again, we get this discrimination result and this ranking scheme. And so here I'm saying this more formally. We have a supermodular game. We can apply the ranking lemma. This is just saying that we're going to have an optimal scheme be a ranking scheme the way we define it. So we are going to define a permutation of the set of agents, and each agent in the permutation will be offered a bonus such that he's indifferent between working and shirking, given that those preceding him work and the rest do not. And if agents are identical, again, we get discrimination. We get this prediction that we have a very transparent hierarchy within the organization. So let's take the case where agents are identical. We can also apply to heterogeneous agents. We have discrimination because some agents are going to be treated better than others. And And I think, the mechanism behind is, I find it to be very intuitive, right? So again, you want to provide assurance to these agents that others are going to be doing their share for them to want to do their own share. And so it has to be that I know, these coworkers are going to be coming to the office and exerting effort, so that I also want to exert effort. Otherwise, why would I be worrying about this? I have no chance of succeeding by myself, right? So that's the basic idea here. But as a takeaway, we also get this hierarchy. So we can think of these workers who are given these larger bonus payments as workers who are assigned to higher ranks in the organization and they're offered better terms. And then there are those who are assigned to lower ranks in the organization. And we could refine this by thinking about, if we have heterogeneous workers, is it the higher skill, lower skill? What are the implications about the rents and so on? But I want to tell you about something else. I want to tell you about how this result relies on an assumption we have made, which is that contracts are public. So in everything that I have said so far, I have assumed that the contracts that the principal offers are publicly known by everyone. And so we got that prediction of a very transparent hierarchy in the organization. Everyone knows that Jan is assigned to a high rank and offered this high bonus payment, and then others are assigned to lower ranks. But when you think about transparency, when you think about discrimination and transparency, these are all very important questions for organizations, right? So first of all, firms don't like transparency. Firms don't make public what are the different contractual terms of their workers. And in fact, there are studies showing that not only this information is not public, but also workers report that they are threatened to be fired if they share their contractual terms with other coworkers, even though this is illegal in most settings. The firms don't like transparency. Moreover, when we think about discrimination, there are efforts to increase transparency that are often motivated by the goal of reducing discrimination. So we think that transparency is good to reduce discrimination. But I just show you a result where we had transparency, we had public contracts, and I got discrimination. So I'm a little bit uncomfortable now about what this means here, right? So I would like to understand what are the implications of these contracts being public for the firm's cost, because I know firms don't like transparency, and for discrimination. So that's what I want to do next. So how are we going to do that? So that's something that I studied with Elliot Limnowski and Daniel Rappaport in this recent paper. And so I want to go back to our simple example, and I want to introduce private contracts in the simplest possible way. Okay? So this is exactly what you saw before. This is just the case of public contracts, right? Our two-agent example. Let me just remind you that with public contracts, the optimal scheme is one where we offer this high bonus payment to one agent. That makes it dominant for this agent to work. That provides assurance to the second agent, right? And so the second agent now is willing to work even with a low bonus payment. So now I want to think about introducing private contracts as follows. This is the smallest change I could make. Let's say that for one of these agents, we offer a private contract. So this agent is going to get either the high bonus or the low bonus. These bonuses are defined the same way as I defined them before. The high bonus makes it dominant for this agent to work. The low bonus makes it, makes the agent willing to work only when he conjectures that the other agent is also working. So let's say this is agent one. Agent one knows what bonus he's being offered, right? So I know my own contractual terms. The principal knows what bonus she's offering to this agent as well. But agent two only knows that agent one may be offered the high bonus or the low bonus. I don't know, right? Agent two doesn't know which bonus agent one was offered. He only knows that agent one was offered either bonus with equal probability. So now we have private contracts. All right, so now let's think about agent two. What is the worst case belief that agent two can have about the effort choice of agent one? Well, the worst case belief agent two can have is that agent one will work, which has a probability of half. Because with probability of half, agent one was offered this bonus that makes it dominant for him to work. So then he's working. And with the remaining probability, agent two may think, no, he's not going to be working. So now I can define this bonus, BM for medium, that makes agent two willing to work, given that belief, given the belief that agent one is working only with probability of half. Okay? All right, let's offer that bonus to agent two. Now I'm going to claim that these bonuses are going to uniquely implement work by both agents. Because the high bonus type of agent one will be working, Given that, agent 2 will be working with the medium bonus. But given that agent 2 is working, given that he has the medium bonus, now the low bonus type of agent 1 also will be working. Okay? So the unique equilibrium here is that both agents are going to be working. But it works differently than in the case of public contracts, because instead of having one agent provide reassurance to the other, now I'm building this assurance in a more mutual way. It's like the high bonus type of agent 1 provides assurance to the second agent, and then the second agent provides assurance to the low bonus type of agent 1. Now, why this is interesting? Well, we get two results already from this very simple example. First, we can show that this medium bonus is lower than the average of the high and low bonuses. So what this means is that this contract is going to imply a lower cost for the principal compared to the public contract. So by introducing private contracts, we lower the cost to the firm of uniquely inducing effort. And moreover, there is a reason why we call it medium. The medium bonus is between the low and the high. And so that means that we also reduce discrimination, both ex ante and ex post. We reduce discrimination. The difference in the bonuses that we are offering to these two agents who are identical has gone down. So this is already telling us that private contracts, by reducing transparency, can mean less discrimination and lower costs for the firm. Now, this is not an optimal scheme here. This is just an example. In fact, the optimal scheme is going to eliminate discrimination. So we have, I trust, 15, so we are good. So I'm not going to show you the details, but I just want to give an idea of how we proceed here. Maybe I'll say some things that, just for the theories in the audience, but I'll be very brief. We want to introduce private contracts in this paper. So the way to think about this is that the scheme now is going to specify some profile of types for the agents. Okay, so we are going to, we want to give private information to the agents, so we need to give them types. Right? So we are specifying some distribution of type profiles. And we are specifying a bonus rule that is going to map from the type of an agent to what is the bonus that this agent is going to be offered. And so this is formally how we can introduce private contracts. Each agent will know how much he's being offered in terms of the bonus. But agents may face uncertainty about the contractual terms that have been offered to other agents. This uncertainty will be given by the correlation across these types. Okay, so this formalization of the problem is going to embed public contracts as a special case. And then what is very nice about this, again, I won't have time to show you the details, but I've been talking about this ranking lemma. We can still get a ranking lemma, right? So we wanted to get a ranking lemma. We want to try to apply the same rules, the same tools as before. But it's going to be a different ranking lemma. It's going to be now one where the ranking is going to be uncertain. So a ranking scheme is going to induce some distribution over agent rankings. And then each agent, knowing his own type, knowing his own contractual terms, will have some belief about what is the realized ranking. And what we show formally as a more theoretical result, that is going to be the key result for everything that we get from there, is that the principal's problem reduces to optimizing over the average ranking. So basically what we show is that it's suboptimal for the principal to give any private information to these agents about what the realized ranking is. And so that's going to allow us to pin down what is the optimal limiting bonus distribution for any optimal contract sequence. So this is a problem that doesn't admit a minimum when we think about minimizing the principal's cost. So we characterize optimal sequences of contracts. There is a unique distribution of bonuses to which any optimal contract sequence must converge. And so, as I said, what we get is that there is no discrimination when agents are identical in the limit. And as a result, what we have here is that the principal strictly benefits from introducing this rank uncertainty. So now let's go back. I said some things as I wanted to give some insight to the theories in the audience, but let's go back now to the predictions for organizations. I said before that under public contracts, we had this very transparent hierarchy. Everyone was assigned to a different rank, right? Every agent was in a different rank. They all had different bonus offers. Now what I'm showing you is that by reducing transparency, by allowing for private contracts, we are going to have a different type of hierarchy. We are going to have, and I'm not showing this here, but in the paper we show, we are going to have that agents who are similar to each other, and for sure agents who are identical to each other, are going to face this rank uncertainty. I don't know whether you are ranked ahead of me, whether you are getting better terms or not. And so this is like we are assigned to the same hierarchical level, and we face uncertainty about the other workers' contractual terms, those who are in the same hierarchical level. But then agents who have much higher skill, we show that they're going to be publicly assigned to higher ranks and offer better terms, better rents, given their skill. So we get a richer prediction in terms of what the hierarchy in an organization is going to look like. Now, going back to the point about discrimination in particular, what the paper is showing is that lack of transparency from the viewpoint of optimal incentive provision is not what drives discrimination. Right? So that can tell us that either these efforts to increase transparency will be counterproductive at reducing discrimination, or perhaps more likely, that if they are not, the reason for discrimination was not optimal incentive provision. Right? So we can think about taste-based discrimination and other things, but for sure, the provision of incentives is not going to be the reason for that discrimination when we think about the relationship to transparency. All right, so let me use the last minutes that I have. I'm going to skip this. To tell you about this last paper. This is the most recent paper that I have with Elliot Linowski and Daniel Rappaport as well, where we want to think about a monopolist problem. So I want you now to think this is going to be a different problem, but the theme is going to be very similar. And this is going to touch on some of the things that we said yesterday. As I said, Jan gave his presidential address, and we were talking about how important these network externalities are for all the tech firms. And so we want to think about a monopolist who sells a good to a set of buyers. And there are two key features. The first one is network externalities. And so this is what we've been talking about for the whole hour. I'm going to assume that the benefit that a buyer gets from buying this good from the seller is increasing in the number of other buyers who also buy the good. But now we have another feature that I'm counting it as a second feature here, but it would be the first one you would think about when you think about the monopolist problem, which is hidden information, right? The monopolist problem, the key feature of the monopolist problem is that we have hidden information. So the benefit that a buyer gets from buying the good from the seller depends on some individual characteristic that is private information to this buyer. This is very different from the things that I said before with private contracts. There, the principal didn't face any incomplete information. The principal was introducing incomplete information. But here, the seller faces incomplete information. I don't know what is the buyer's willingness to pay for the product, even when I condition on how many other buyers will be buying the product. All right, so this is different from what we did before. And I want to claim that this is a very canonical setting that has many applications. You can think of this seller as the seller of your favorite good with network externality. So we can go back to all the tech firms, right? We can think about online multiplayer games. We can think about social media platforms. We can think about payment apps. We can think about file sharing services, dating websites, whatever you'd like, right? So we have all these network externalities, and for sure we're going to have private information on the side of the buyers about their willingness to pay. You can also think about my investment problem, right? I could introduce private information by thinking that investors have private information about their other planned investments and hence about how this particular investment with this firm would be attractive to them. So there are lots of applications here. And the question we want to ask is, what is an optimal pricing mechanism that maximizes the firm's revenue? So we can think about more complicated mechanisms. The theorists in the audience are thinking, well, you have incomplete information, why don't you offer menus? It turns out in the model that we set up, that would not improve things for the principal. So it's without loss to look at just the principal offering prices to these buyers. And so that's what I'm going to look at today. And so the principal, the seller here is going to make a price offer to each one of these buyers. I'm going to allow for personalized pricing, okay? So I can send you some discount in the mail, and that's just for you to use. And so I want to think about what is an optimal distribution of prices. So because we have little time, I'm only going to give you a teaser example, and I'm going to end with this. So let's think that we have a unit mass of buyers. They have some types that are drawn from the uniform distribution from 0 to 1, okay? And if a buyer buys from the seller at some price, Pi, and the total purchase quantity, namely the total mass of buyers who buy from the seller is given by Q, then this is the utility that the buyer gets. He gets his type times Q minus the price he pays. Very simple example. So the question is going to be, what are these prices PI that the seller wants to offer to each one of these buyers? So the seller is going to make price offers, and then these buyers are going to simultaneously decide whether or not to buy from the seller. Okay, that's the problem here. So I'm making these price offers, and they simultaneously decide whether to buy or not from the seller. And the seller wants to maximize her revenue. That's all. That's all we're asking here. Now, let me note that the seller wants to guarantee a high revenue. So if there are multiple equilibria, the seller will be concerned with the worst case equilibrium here, the lowest quantity equilibrium. If the types were observable rather than private, then I could apply all the tools that we had before, right? But the problem here is that these types are unobservable. So even when I condition on how many other buyers will buy, I don't know what is the willingness to pay of any one buyer. So I don't know what price I need to offer to any one buyer to make him indifferent between buying and not. Right? Okay, so now, as I said, I'm just going to give you a teaser example. So if you have to ask this question, what are the prices that the seller wants to offer to the buyers, the first thing you will think about is, well, why don't you just post the price? Why don't you offer the same price to everyone? Just post the price and that's it, right? Well, it turns out that if I was thinking of this powerful seller who is able to select what equilibrium is going to be played by these buyers with the posted price, then a posted price would be the optimal mechanism for the seller. So if the seller can choose what equilibrium will be played in the induced game, then a posted price is indeed an optimal mechanism. This is an interesting result in itself because we know that without externalities, posted price mechanisms are optimal. So this is telling you that if we introduce network externalities, but we allow the seller to pick the equilibrium, we still have a posted price being optimal. It's not going to be the same posted price, but it's still a posted price. Okay, and we can solve for what is the optimal price in this little example. Now, the problem, of course, is that if I have a posted price, I'll also have an equilibrium where no one buys. I have assumed here in my payoff function that if a buyer expects that no one is going to buy, if I expect that no one is going to join this online game platform, then who am I going to be playing games with, right? I don't have any willingness to pay for joining. And so, of course, for a posted price that is strictly positive, I will have an equilibrium where no buyer buys. That gives a revenue guarantee of 0. If the posted price is 0, the revenue is also 0. So a posted price is a very bad idea for a seller who is concerned about worst case outcome. The revenue guarantee would be 0. Okay, so then you say, well, one price won't do it. How about just 2 prices? Let's take some share of the buyers and say, hey, you get the good for free. You are in, okay? So you are in the platform, you are getting the good for free, you are willing to join. And then let's take the remaining share of the buyers and say, now you have to pay. So let's set that price so that even if they assume that only the first share of buyers is buying, some of them, depending on their types, will be willing to purchase. Okay, so we could just do 2 prices. Some people get discounts, some are full discounts, some other people don't get any discount. Well, then we can guarantee a positive revenue for the seller. That's good, right? We can guarantee that there is, the worst case equilibrium has some quantity being sold, and we can solve for what is the optimal revenue. What is the revenue in that case? But why 2 prices and not more, right? We could do a continuous distribution of prices, and we can solve for what that gives us. And we could continue with trying different distributions. Eventually, we ask, okay, what is an optimal price distribution? And so here is what we get. In this little example that I show you, but with features that are going to be true more generally, what we get is that the optimal price distribution is uniform up to a mass point. And so this takes this form. The seller is going to post the price. Okay? Some buyers are going to get no discounts. You just face the posted price. Depending on your type, you may want to buy or not. But then there are going to be all these dispersed discounts. Some buyers are going to get a very generous discount, a full discount. Some others are going to get a less generous discount. And so this idea of a posted price with dispersed discounts is actually something that we see in applications a lot, right? There is indeed a posted price, but then you have different opportunities. Some buyers have different opportunities to get promotional deals and discounts. And we can pin down exactly what this distribution is. And so the idea here is that this price distribution is serving 2 goals of the seller. On the one hand, the seller wants to exclude bad equilibrium outcomes. So the seller wants to exclude the possibility of these outcomes where buyers think that others are not going to be buying, so no one is going to join this platform. I don't want to join this platform. How do I make sure, how do I insulate myself from that bad outcome? Well, I have to, convince some buyers to participate, right? And so I do that via these discounts. But once I have ensured a high demand for my product with network externalities, I also want to extract revenue from that high demand, right? So I ensure high demand. How do I extract revenue from the high demand? Well, we know the best way to extract revenue is a posted price. And so that explains that mass point. And so in the paper, we show more generally what is a revenue maximizing mechanism for the seller that is concerned about worst case outcomes. And we show that indeed it takes this form of this posted price with dispersed discount, and we relate that to applications. And so the seller sees the demand from the bottom up to this extraction point, and we also use this solution to shed light on, how the price distribution changes depending on the strength of externalities and things like that. All right, but I think I should conclude. So I hope I have convinced you that this problem of contracting for coordination arises in many different applications. The coordination problem gives rise to the possibility of multiple equilibrium outcomes, and that calls for a robust approach. So what we did today is study the principal's optimal worst case implementation scheme. How would the principal want to contract with these agents, given her concern for strategic uncertainty, given her concern for these bad outcomes? And what we find is that there are implications for the contracts that the principal wants to offer, contracts in markets, prices in markets, contracts within organizations, and also for the outcomes that are going to realize when we think about the implications for things like inequality and things like that. And I think there are still many open questions. So maybe some in macro, I have to think about that after Jan's introduction. And I have included here in case any students would like some. There are lots of references, more than the ones I could cover, but I think that's all. Thank you very much.
We have time for some questions. Massimo.
Yes. Oh, very good. Fantastic presentation of this very important work. I have a question that relates to regulation, because, of course, the first impulse would be to say, of course, there will be regulators that are interested in reducing discrimination, reducing inequality. That's a kind of obvious. But then, of course, your result that optimal private contracting eliminates discrimination, and to some extent, in some applications, also inequality, says, well, don't worry about it, because we are looking at optimal private contracts that work well also in terms of discrimination. But what about a regulator that is interested in innovation, in entrepreneurship that could be dispersed? So you could imagine that in any given period, the distribution of types relates to the technology of that period. So today it may matter, information technology, distribution of skills. Tomorrow it could be biotechnology. The day after it could be something else related to surveillance, AI, whatever. So the distribution of types of productivity of different agents changes depending on the project of the day. Therefore, even without discrimination, that is, even with a contract that within today gives an advantage of bonus to the one which is highest type today, if the accumulation of differential bonuses today influences somehow in the production function of the future, also who is going to get financing for a project when a different type of skills matters, may make the regulator be maybe in favor of a public contract that reveals at least partially which type of dimension of skills is going to be rewarded by the bonus scheme.
I think I managed to. Does it work? Okay. All right, that's a very rich question. I'll need to think more about it. Many moving parts. But yeah, so for sure, I think there are different reasons. When we talk about private contracts, it was really the principal introducing this private information about the contractual terms. I think you are thinking about a setting where that gets combined with some private information about primitives that we might care about, right? For example, because of innovation.